Well, hello everyone, and welcome to AWS OnAir Data Dive. This is a show where we dive deep and get those shiny data treasures for you. I'm your host, Aditya Samant, reporting to you live from rainy Dallas, Texas. It's actually been raining all day here today. Let us know in the chat where you all from. How's the weather out there? And today's topic is, drum rolls please, it's Gen AI. Yes, generative AI. And we're going to talk about some of the cool technologies that Amazon lets you use to take advantage of generative AI. We're going to talk about databases. We're going to have some fun. We're going to look at some demos. As you all know, I'm not an expert. I'm just here to ask, fun questions and make really these guys look, these guys look good, who are the experts for us today. So we have Jonathan Katz, who is a product manager coming directly from our service team. He is the maker of things, keeper of secrets, and user of props during demos. So you'll see that in a minute. And I also have a colleague of mine coming from our specialist SA team, my good friend, Shayan Sanyal. Well, at least I think we are friends. So let's get those introductions out of the way. Shayan, are we friends?
We'll see. We'll see about that. Let's get the show started. All right. So hello everyone. Thank you for dialing in from wherever you are. My name is Shayan Sanyal. I'm a part of Aditya's team here, and I also specialize in databases. So welcome everyone. It's great to have you. And of course, in my day-to-day role, I talk to a lot of customers about everything Postgres, but lately the topic has all been Gen AI. So happy to be here, excited to be here. I'll hand it over to Jonathan to do a quick intro.
Hello, Jonathan Katz, and I want to make it perfectly clear up front, Sharon is my friend. Maybe Aditya, one day we can be friends, but for sure Sharon and I are friends. I would love to be your friend. But in addition to being Shayan's friend, I'm a principal product manager on the Amazon RDS team, focused on all things Postgres and often like a lot of other things, databases as well. I'm actually active in the open source Postgres project. I'm on the core team, which is it's hard to call it like the general governance body. It's sort of like when things get escalated high enough and no one else can come up with the decision, the core team does it. But a lot of my day-to-day is involved in other aspects of the project, release management, governance, etc. But one of the reasons why I love talking about Gen AI is I've become very active in the PG Vector project, which we're going to talk a lot about today.
Excellent. Well, as everybody knows, I don't know much about Gen AI, I'm sure there are folks who are the uninitiated, so to speak. Jonathan, can you tell us a little bit about Gen AI? I hear you come bearing slides, so maybe we can share your screen and you can talk about some of that stuff.
Yeah, well, let me set it up, and then I'm going to share some slides where Sean will start walking through as the database expert. But Gen AI is definitely something that's like transformed the imagination, because where it starts is like if you look at like AI and machine learning, these are not new things. Like we were doing AI back in the 1970s. In fact, when I studied when I was in college, which wasn't in the 1970s, but a little bit ago, I actually was studying machine learning. And what was interesting is that when you looked at these machine learning models, a lot of them were very complicated. They could just take vast amounts of data and be able to turn it into representations where you can make predictions on it. But they tended to be trained on smaller data sets, and like the amount of inputs or dimensions in them were far smaller, in part because we were restricted by computing power and storage. But computing power and storage has certainly expanded, right? Like we see that right here at AWS.
Leaps and bounds. I remember the Pentium 2s of my time.
Pentium 2, that was huge when Pentium 2 came out. I think that's when I was becoming of age with computers. I was like, wow, it's amazing how fast this chip is. But now we have, CPUs and GPUs, graphical processing units, that can do like these hugely parallelized computations, which are essential to build up what we call these foundation models. Because of all these advances, we're able to design these machine learning algorithms, as part of generative AI, to build these foundation models. And like what I like to think of a foundation model is like, imagine like a giant data set, like the entire internet. You can take this model, like literally read in the entire internet and build all these inferences around them, sort of like how like a human brain works. And then from these inferences, you can make predictions that sound a lot like a human talking. And that's the generative part. And what's really cool and what we're going to see today is that there are a lot of these pre-trained foundation models where you can take your existing data and tie it into the data in these foundation models and give like this really rich content answer. I think this is what Cheyenne's going to show to us right now.
Well, I mean, that all sounds great, right? Like, I mean, I'm just happy that you talked about GPUs because that's really the only part I know. But Cheyenne, you're our database guy, man. What does that have to do with databases?
Yeah, absolutely, right. So imagine like these LLMs that we just talked about, the large language models. Very popular example is ChatGPT, right? So these models are really trained on public data, right? Which means there's only so much that you can do with it in practical day-to-day real life. Imagine now if you had a robot who was trained on doing things meticulously in your house, like clearing your floor or like putting your slippers back or making coffee for you as per your unique preferences. Wouldn't that be nice, right? So in this
Yeah.
example, imagine like you're a travel booking company. We are talking about like the Expedias or the TripAdvisors of the world, and your customers are looking to book a hotel for their next vacation to Hawaii. And as a customer, my customers would come in and ask a question. Let's say, like, I'm looking to book this hotel near Maui, which is like a very popular holiday destination. Now, I don't know how much this costs. So I really want a tailored cost to my profile, given the assumption that I've signed up for some discount programs. Probably I'm a loyal customer to this hotel. So with public data on the LLM that this model is trained on the world of knowledge that it is trained, it may not really know the answer. Or it may have like a knowledge cutoff, which is what we call as stale data.
Yeah.
Worse, it may even hallucinate, which is where it tries to make up a incorrect response on a question that you never asked it.
Wait. What
Mind
do you
you,
mean hallucinate? Wait, isn't
yeah,
that like a human thing?
it is. It is. Certain medicines and you start hallucinating. Just kidding. But yeah, of course, there's if you think about scenarios where you want the model to respond to a unique response based on your profile, maybe it's your customer data, maybe it's your company data, maybe it's your travel profile, and let's say like it'll give you a unique tailored cost based on the programs that you've signed up. Maybe for this hotel in Maui, my unique price is actually $499 a night. Whereas if I search on Google, it's actually costing me like over $1,000. It's a very popular destination. That's not what I want. So rather than hallucinating for a wrong response, which is maybe it's just spilling up a lake near Maui and giving you a lake as an image in the response, you never know. The responses are actually interesting, mind you, but
Yeah.
that's not what we want, right? So we
Yeah.
want very tailored responses based on the model and the knowledge that it is trained on, which is what brings us to the topic of knowledge bases.
Well, there's a question here, and someone wants to know what is an inference. One of our SMEs actually addressed that, but maybe we can touch upon that real quick.
Yeah, absolutely. So these the large language models or the foundation models that we just touched upon, they are understand that they are trained on humongous volumes of data, right? So it takes years and years and years of training and a lot of compute with those GPUs, etc. And this is where Pentium 2s will not actually cut the bill. So, right. So you need a lot of horsepower to actually train and make it ready for just like general knowledge information. Right. So the way the LLMs or these foundational models or these just more generically the machine learning models respond to these questions is basically by inferencing. They have this data set on which they're trained, then they do make inferences on this data set. So essentially pulling the right chunks of the data, pulling the right paragraphs from that. If it's a text document, pulling the right paragraphs from those chunks to generate that answer to a human eye, right? To a human natural
Yeah.
language response type. That's
Yeah.
Yeah,
basically what inference is.
Maybe further, like Cheyenne, you just did an inference. You had a question, and you
Yeah.
gave a response, and that's effectively what the inference is. Is that based upon the question, you search through that knowledge. It could be like in your brain, or in this case, it's through these foundation models, and that's how you determine your answer.
Yeah. So
Absolutely.
let me get this. Let me make sure I got this right. So you have all of these large models. They are
Mhm.
trained on maybe data that's not relevant to you. Then here comes your database, and there's data that's relevant to you, and then you kind of augment it. Right? See, nothing gets past
Exactly.
me. It's a retrieval augmented generation. All right. Well, that sounds cool. So What else? What else you got, Jonathan, about this?
So I think one thing that we need to capture here is what do vectors have to do with it? Because you mentioned this PG vector, you mentioned this vector, but we haven't really dove into it yet. But
Yeah.
if you look at this screenshot here, what we need is we need a way to take that knowledge that exists in a database, which is often stored in like text or chunks or integers, and be able to convert it into this answer. So we need a common representation, and that's where the vector comes in. Because a vector is just a mathematical structure, and within it, we can use it to capture specific information. And there's actually special models called embedding models that can take a bunch of text and turn based upon all the data it's been trained on, it can find similarities in that text and output a vector, which is a way that we can compare things to each other. So I'll do. You said I like to use props, so I'll compare like these two cars, right? I have these two cars on my desk.
Yeah.
One's a Lamborghini, one's a Porsche Carrera 911, and if we look at it, we're going to say, well, we can get very specific. I gave you the makes and models, or we can abstract it further out and say these are cars. So if we turn these into vectors, we'd be able to figure out like how close they are to each other in what's known as a vector space in terms of how similar they are. So, overall, we know that these are two different kinds of cars, but in general, they're cars. And, we would probably say that they're fairly similar to each other versus, say, this cat. I have a cat. It was actually given to me as a gift I won as an award, which apparently the person said it resembled my personality. Well, from there.
Were they saying you're catty?
Yeah, maybe, or a little grumpy at times. But if I were to like take that same cat, put it through the embedding model, and get a vector, we probably see that the cars and cats are different, and that if we're to do a comparison to see how close they are to each other, there would be some distance between them. And that's the fundamental thing that's going to be going on in what we're demoing today, is that we're basically taking these objects, turning them into vectors, and comparing them to see how similar they are through what's going to be called a distance function. Because we can see right here, there's definitely distance between these objects. Now, the key is that we have to be able to take this information and transform it into a vector for later use. And this is where I'm going to turn it back over to our database expert to explain how this works in something called retrieval augmented generation, or RAG.
Absolutely. So you saw a buzzword, and we touched upon it, Aditya, the RAG, retrieval augmented generation, and I'm sure you're learning way ahead of the curve here. So let's touch upon this, right, a little bit. So the basic process is you have a source set of documents. You'll have like structured data, you'll have unstructured data, etc. You upload it to some data store. In this case, could be S3, could be like a flat file sitting on somewhere on your local desktop, doesn't matter. But then what happens to this source data? It's not really readily understandable by the machine just yet, right? It's a whole bunch of text. These are texts in maybe like English or Spanish. To the machine, this actually makes no sense. So we need it to be converted into a format that is easily understandable by the machine first, and eventually it has to be read back by the human. So it has to be encoded and then decoded back to a language that the human can understand. So this is what we do here. We actually upload a file. Let's say it's a PDF document, could be an image, could be an audio, could be a video, doesn't matter. Then we go through this whole process of chunking the document. And why this is important is because anytime you're asking a question, it'll usually be like a very specific question. It's not like, give me the list of all the wonders of the world, right? It's going to be, give me one wonder, which is where I should plan a visit, maybe end of this year. So we're looking at very small bodies of text or images or documents, etc., as compared to the whole body of, like, if it's a 5,000 page book, we're actually not interested in retrieving the full book, versus we are just looking at certain chunks within that book. So that's where chunking comes in. And the next thing we do is we vectorize these, which is where we call these, basically, we use an embedding model. There's a lot out there. Within Amazon, we provide Amazon Titan as our family of embedding models. There's a few different ones from third parties as well, like Cohere, etc., which are basically now vectorizing this human-looking like text or image, etc., to a numerical representation.
So there's a question here, and folks are asking, how many dimensions can you have to a vector? So I guess maybe we can talk about the context of PG vector then.
Yes, absolutely. So the dimensions are really, it will be determined by the model that you're using. every specific model will have its own set of dimensions. It'll come with its own number of numerical representations that it can represent and the attributes associated. Right. So a very popular one on the open source space is sentence transformer from BERT on Hugging Face. It's like a 768 dimensional model. Within the Titan family, we have Titan Text V2, which is a newer version, which has 1024, 768, 384. You can actually customize it to your use case. Whereas the larger ones are also available. So Titan Text V1 is actually 1536. So there's a lot of models out there, and it'll always be a choice tied to the model of your choosing on the number of dimensions.
Okay.
Yeah. So in this pipeline, the next thing that we then do is sort of store this numerical devectorized data into a vector database. In this case, it could be a knowledge base, it could be an Aurora Postgres database with PG vector. And then we do something called as a similarity matching, right? Semantic matching or similarity matching with the user question. So the user question comes in again as a human like English question or a Spanish question. And then the question itself again gets vectorized with the same embedding model. There's a key point to note that it has to be the same model. Otherwise the distances get all screwed up, right? So once you do that, you ask a question, you match it on the document based on the similarity. And in this case, we can use something like a cosine distance. And then we are basically augmenting the responses of that question from the knowledge repository in the database, in the knowledge base, and doing a response generation back into a plain, simple English-like language via the large language model.
Yeah, that all sounds really impressive. I think now I kind of have the secret of how you're getting all those Maui trips, right? You're using all this cool tech here. All right, well, Jonathan, I think enough talk. Would love to see some demos here. Jonathan, what you got for us?
Sure, that sounds great. Let me pull up my screen real quick.
Can you get Jonathan's screen up, please?
Alrighty. So how do we actually put this all into practice? We want to book Cheyenne's Maui trip. That sounds awesome. And we have this service at AWS called Amazon Bedrock, which provides foundation models as a service. It gives you a choice of foundation models based upon your specific problem domain. There's foundation models that are more text-based, vision-based for images, and some that combine both, like the new Claude 3 models. And what's great about the Amazon Bedrock foundation models is that they're serverless. So basically, you only use what you need to use, so to speak. You use it on demand and can use as much or as little as you want. And these foundation models are already pre-trained on the data, so you don't need to worry about training them on your own. You can you can use that retrieval augmented generation technique we just saw to take the information and apply to those foundation models. What's really cool is that Bedrock has a feature called knowledge bases, which helps to create a no-code solution for being able to add this in, which is great for me because I used to code a lot, but I can tell you outside of SQL, I've gotten pretty rusty at my coding. So let's take a quick look at what Bedrock looks like when you go into the console. If you say get started, it shows all the different foundation models you can explore and learn and become familiar with in order to build out your generative AI application.
Well, I see a bunch of models there. I recognize that's Meta, right? Meta Llama.
Yep. Yeah. There's a whole choice. There's Mistral, which is an open source model. There's Titan, which we've developed here at AWS. Yeah. There's Anthropic Claude, which we're actually going to look at Anthropic Claude today as part of our RAG app we're building.
And all these models are available to use. We can just
all these models are available to use. You can go and you can enable them in your account. There's a feature called Model Access where you can go and you can select which models that you want to use for your application.
That's cool. And then I really liked what you said, right? You only pay for what you use. So if you were to do this yourself, that could get pretty expensive. It sounds like these are just API calls.
Yep, just simple API calls.
Excellent.
Which again, that's probably the limits of my development abilities today, writing SQL and making API calls.
Same here, man. Same here.
But the feature we're going to look at today in depth is called a knowledge bases. I've actually already built out a knowledge base, but I want to show you briefly how you would go in and create a knowledge base. So recall from that that first slide we saw, the knowledge base is effectively your database. It's that information that you've built up that you're going to use to augment the responses from the foundation model. So basically create those responses that contain your, that private data that you've built up.
Yeah.
And to create it, you would go in and you click create data, create knowledge base. It gives you several options, to name it, add a description. And as you go through, you would go and you select an S3 bucket where you'd have data that already exists. Or maybe it doesn't already exist. This is the data you're going to upload your PDFs or unstructured content to. From there, you would choose...
So I could just add like a doc file or PDF or whatever. Oh, that's excellent.
Spoiler alert, we're going to do that today.
Oh, nice. All right.
So then there's a couple of things you can do in order to finish setting up your knowledge base. So the first thing is you select your embedding model. So there's an option available right here, and you can choose to either quick create a vector store or you can choose an existing database. Today we're going to use Amazon Aurora. You fill out some information about the Amazon Aurora database that you've already created, and then you're off and running. What happens is that Amazon Bedrock is going to create an automatically managed RAG pipeline. So whenever you upload data to your S3 bucket, it will automatically be split up into chunks, turned into vectors through whatever embedding model you choose, and stored in your Amazon Aurora database.
Okay.
So like Julia Child, I put the turkey in the oven, and then 1 minute later I take it out and it's fully cooked. So I've already set up one of these. I have an S3 bucket, and in this S3 bucket, I've uploaded a document called Postgres 16. Why Postgres 16? Because Postgres 16 was released in September, and when a lot of these foundation models were trained, they would have no knowledge of what was in Postgres 16, including the highlight, such as like the highlight features of it. So I'd already had uploaded it, and I've actually already created a database, which I'll show you. It's an Amazon Aurora Serverless v2 database where I have these vectors stored. And within that, I've actually also opened up a query editor where I've been running queries against it, and we'll get a little bit more into that. But I want to show you the magic of using the knowledge base, because for me, this is the coolest part. So in this knowledge base, we can actually test it out, and we can use different foundation models in terms of how we want to test it. So I click this test button. What I can do is I can select a model, and I'm going to choose one of the newer models, like the Claude 3 Haiku. And I'm going to ask a question. I'm going to ask, say, what are the highlight features of Postgres 16? Let's see how well I can type. That's the test.
Well, what I like is it seems like everything we use here is serverless, right? Like I heard Aurora serverless. This whole thing is API calls, so sounds like we're just only going to pay for those API calls. That's fantastic. Yep.
And here we go. We get the answer. Again, this is the test interface, right? In a real application, you dress it up a little bit more, but you can see like the highlight features are yada yada yada. I know this is accurate, by the way, because I wrote that for the release announcement, the release notes. So these are the highlight features of Postgres 16. And what's cool is in this debugging mode, we can go in and we can see the source chunk, basically the text that was used to help augment the response to it. So this gives us like a lot of information we can look at into it. But let's see how.
Zoom in a little bit, Jonathan. Maybe it's a little bit blurry here.
Sure. Is that better?
Yeah. That looks
all
good.
Right. Cool. So now I'm going to test this, and I'm going to show. We're going to see. I'm going to do like what everyone loves to do, which is the live demo, and see if it actually works. We recently published a blog post called "How Aurora Optimized Reads Can Help Accelerate Vector Queries." And what's really cool about this feature is that for workloads that exceed your database memory, which can be quite a bit, Amazon Aurora has this feature called Optimized Reads that uses the local disk, the local SSD that's on the instance, as a place to keep data that's recently evicted from memory or pushed out of memory, and it keeps it at that layer. So that way you don't have to go all the way down to storage, which can be very expensive, but instead it keeps it at that local layer. What's great is that vector data tends to be immutable, which is a fancy way of saying it's not updated very often. And because of that, it makes it very easy to stay in that layer, and it can help speed up queries, up to 9x for workloads that exceed memory.
Wait. Did you say 9x?
9x.
I don't believe it.
Nine times. Well, I could show you a graph later on it. But
let's see the graph.
But let's see. Well, first let's ask the question. Like, is Claude aware of this? So, how does Aurora Optimized Reads accelerate vector searches?
Ooh, someone is saying, is that faster than Pinecone? My question is, what's PineCon?
So there's a lot of different ways. Actually, while I set this up, I'll answer this real quick. So there's different places that you can store vectors. There's emerged a class of databases called vector databases that are specifically for vector search. For me, a vector is just a data type. So if you have a database that can store a vector and implement an index, you have vector similarity search, and that's in part why we offer vector search across a wide variety of our portfolio of AWS databases. Amazon Aurora, Amazon RDS, both Postgres engines, Amazon OpenSearch, Amazon Document DB, Amazon Memory DB. So it's all. So we have it all over the place. And and I forgot Amazon Neptune Analytics as well. And this is great, right? Because we want to make sure that we're putting vector search at the place you're building your applications. Because builders use all sorts of different tools, and we want to make sure that everything we do is compatible with how you're building it. So as we can see here, Aurora optimized reads, we asked this question and gave an answer that's not really related to vector search. Like this is not relevant, but we can make it relevant. So what I'm going to do is I'm going to upload the blog post that we wrote that shows that 9x number that we're talking about.
Oh, cool. So you can upload web pages too?
I can. Well, in this case, I saved it as a PDF.
Oh, okay.
And for some reason, my drag and drop is not working. All right.
So remember, this is always going to be like an S3 bucket, right? So there are multiple formats that can be supported. Yep. But also
so no direct web page, but you can dump it into like text or whatever, or PDF.
Exactly. You
Makes
could
sense.
have a CSV, you can have an Excel, you can have PDFs. PDFs are pretty heavily tested. I think they work really well. So PDF would be a good way to go.
So now what I'm going to do is I'm going to sync the knowledge base. So I'm going to do an explicit sync. You can actually do an automatic sync. So every time you add data to your S3 bucket, what it'll do is that, it'll either create the new embeddings for the new data that you added to it, or if you remove documents at the same time, it'll remove those embeddings from your database. So that's pretty cool because you can keep everything up to date. And we see that the sync process is running right now, and it's handling all the updates in our database.
Nice.
Yeah, it's
So
generally pretty quick.
if you were to do this yourself, that would be pretty code heavy, right?
Correct.
If you were not using like this Bedrock right now.
Correct. The idea is that this creates a low-code, no-code way of being able to automatically keep everything in sync. And this is great, right? Like I get to talk to a lot of customers about this, which is like actually one of my favorite things to do. It's like I love hearing what people are building because it makes me pine for the days where I knew how to build things. But what's really cool is like one of the big requests is like customers just want to manage pipeline for this. A lot of what they have to focus on is how they're building their generative AI application. They don't want to have to worry about getting the data into the database. And this is what knowledge bases really helps with, is that it creates a very, an easy, fully managed way to be able to take the data that already exists and put in the database and manage that pipeline. So our knowledge base is synced. Let's ask that question again. How does Aurora optimized reads accelerate vector searches?
Nice typing, man. I would have definitely made some spelling mistakes there.
Yeah, I think last time I tested, I could do 125 words per minute, but it's been a while. But here's the answer. I can tell you this is from the blog post because, spoiler, I worked with a wonderful team of folks to write this blog post, and here we see, we see the 9x increase in query throughput compared to instances without optimized reads.
Yeah, that's really cool. I mean, it seems like you can choose different models. You can just pump this data in a vectorized form in databases. That sounds like just very easy, just push button things to do. I'm impressed.
Thank you.
I guess we want to see some more interesting demos, some text, and that's great. But maybe some visuals. I think Cheyenne has something up his sleeve. He's smiling.
Yeah,
Cheyenne.
I was just waiting for you guys.
All right, so let's get Cheyenne's screen up and let's do some demos.
Yes.
Because, of course, as you mentioned, Cheyenne is the database expert, but he's also the building expert. And like one thing I love about Cheyenne is that I could be like, "Hey, Cheyenne, I have to go to AWS OnAir in an hour. Can you build out this demo?" And like, boom, he whips it out.
All right, yeah.
Welcome to Animal Kingdom here, everyone.
Excellent.
All right. So one thing we are going to demonstrate, we are going to do two demos today, and we're going to look at something that goes just beyond text, right? So we are these days it's all about multimodality. We're seeing a lot of the human eye actually looks at data that is not just text, but also images. We're looking at videos, we're looking at audio, etc., etc. And it's cliched, but like everyone says, right? A picture is always worth 1,000 words. Have you heard that anywhere? Anyone?
No, I'm hearing that for the first time, man.
I know. I had to just put it out there, you know? So this is the problem statement. So imagine like, oh, by the way, you should say, everyone in the chat, you should say hi to my friends here. There's Toto, who's the brown dog. There's Jack Sparrow, who's the sparrow here. There's Crush, who's the turtle. And there's Miss Hiss. Of course, we're using Python. We have to use a snake, right?
Kid
All
New
right.
York says hi.
Everyone says hi. Cool. So I'm going to give them something to play with, give them a couple of things to keep them busy while we get into this. All right. So what we are demonstrating here is imagine that you're looking for pets, right? So me and my wife, we just started this hunt for adopting a cute puppy. And we are like, not to start any animal wars here, but we are dog persons, right? We are dog people. And we are trying to approach like these different animal shelters who are offering pets for adoption. And your local animal shelter, they want to improve their website's adoption process a little bit by implementing this semantic search based on images, right? That's the use case. So this will allow like potential adopters like myself and my wife to just go in. Maybe we can do a keyword-based search. We can look for, help me look for a puppy of a specific type. Or I could also potentially upload images that will match the catalog of this website from the animal shelter, and I can retrieve similar images. I can do both of those, right? So typically, your images will actually have some images, of course, but then you'll also have these text inputs as part of those images. And in this case, what we're doing is taking that embedding model that we talked about and vectorizing both of them together to generate these numerical representations, right? So let's get into it. I've done a little bit of pre-setup here because it takes a little while to run these blocks. But let's say I just dive right into, I'm looking to adopt, this is the code. I'm looking to adopt a puppy. More specifically, I'm looking for either a golden retriever or a Labrador. Can you suggest some options? Now, please, who's a golden retriever fan? I cannot think of someone who's not, but throw that in the chat.
I love them all, man. I love them all.
I know, right? I know. You are my best friend now. So, all right, let's see. I didn't run the collection before. So let me actually run this code again. Yeah, real-time coding always has some bugs
Technical
and issues.
difficulties. You didn't pray to the demo gods, man.
Yeah. Hey, what is what is this thing called? Like this looks like magic to me. Like, how are you running all this code?
Yeah, so this is via VS Code. This is in Jupyter Notebooks. Very easily available. You can either get it on the marketplace, or we also actually have SageMaker-based Jupyter Notebooks, which is where you can actually spin up this Jupyter Notebook very quickly. There's some dummy code here that you can reuse for your use cases, and it'll get you like up and running in no time, right? So
that's really cool.
It's very easy, actually, for the developer community. It's very easy to get up and running. All right, so I missed a step there to create the collection. I created the collection once again. And this is my query. I'm looking to adopt a puppy. And you'll see I have a whole bunch of beautiful puppies that I can potentially adopt, right?
Nice.
So this is one potential. This is another cute Labrador from this catalog. There's probably some corgis lying around. So I can do that, but then if I also want to see like what else, let's say I'm looking for a multi-poo, right? So let me just go for looking for a multi-poo here. Again, super cute. I'm sure like people will love him. So let's see.
Oh, well, all right. I hope all right got lot many times. I don't know if I got it right, but that's actually a name of a Twitch user. They're asking, is this running locally or are you hosting it somewhere? I think I got that right.
Yeah. So this Jupyter notebook is running locally on my desktop, but the data and everything else is the LLM that we're using is in this case we are using just an embedding model from Titan, which is through Bedrock. The storage, the vector store, which is actually what I'll now take you back to. Uh, Give me 1 second. Is actually Aurora Postgres with the PG vector extension. So if I go here on the command prompt, I'll just demonstrate very quickly what we have, the setup. So we have a Cloud9 environment. I have a Postgres database here, 16.1 on this instance. And then I've created the extension. So this is my vector data type, vector extension. In this case, I have a couple of tables that I'm using, LangChain collection and LangChain embedding. Before I go there, just throw in like in the chat, who here has heard of LangChain? Maybe we'll do a quick debrief on what
I
is
heard it
LangChain.
yesterday from you.
Yeah.
So
So I'm assuming not a lot of folks have heard about it. So LangChain is one of our open source sort of ecosystem toolkit libraries, etc. Right? These are a set of helper classes, helper libraries out there, which have a lot of compatibility with a whole ecosystem. Right? There are multiple document stores that you can use. There are multiple vector stores that you can use. There are multiple embedding models that it supports. And of course, it supports PG Vector, it supports Titan via Bedrock, it supports Claude 3 via the LLMs, etc., again via Bedrock. And it makes it super easy to actually customize your application very tailored to your specific users. Right, that's a developer choice. It gives me a lot of flexibility to build my applications. So that's what it's doing, right? So we are using the LangChain framework to create these couple of tables. Let's actually look at the embedding table for a little bit.
well,
And
you're
where are
actually
we
getting a lot of
storing?
people inspired here, Cheyenne. I hear a couple
Oh,
of
really?
folks. Nakomi is saying that he's going to start right now, or she, and they're going to start using this. So it's a good job.
Perfect.
You're doing good.
Yeah, I mean, all credits to Harrison Chase, right? Mr. Chase has done an awesome job. There's this company like took off, I think, just a year ago, and I've seen like tremendous adoption. So coming back to this topic, we have the embedding column, which is actually where we are storing our data, which is the vector data type, right? So if I do a quick select star from before that, actually, I'll make it a little bit readable. So select star from, let's say, LangChain PG embedding. Just do a limit 2 to fetch the most closer ones. Actually, let me see. Yeah. There we go. You'll see this kind of gibberish here, right? So this is sort of all your vector embeddings. This is the 1024 dimensional vector data sitting here as numerical representations, which is actually what we saw right here on the very top. These are these numerical representations that are getting thrown at the database.
Man, numbers turning into puppies. If that's not magic, I don't know what is, right?
Exactly. So this is what it works like. This is how you look at it. Let's go back here. One more thing I wanted to highlight is imagine like now if you want to just upload an image, right? You imagine, I'm getting a little ambitious here. You probably don't want to do this in real life, but imagine I want to adopt a tiger as a pet, right? I'll upload an image of a tiger that I love, and then I
Man,
can run
what
my
is it with
similarity
you?
search.
You're going to Maui. You have robots at home to do your work, and now you're adopting tigers.
Yes. I'm on a I'm on a pretty ambitious plan here. So
Nice.
there we go. So this is what you'll get from the catalog. You'll actually also see another key metric here. I know it's hard to read. The 0 number here. This actually is the similarity score, right? So what we are doing here is getting a ranked score-based threshold, and based on the threshold, we're actually fetching the closest matches in that vector space close together. So whatever matches my image that I upload, I'm getting the 2 most relevant results from that data set, and I'm populating the vector score. So this is actually an exact match in this case, which has the closeness of 0. So this is exactly what I'm looking for. Whereas this tiger is maybe a little bit different, pixelated, or some different attributes. It's a little bit closer, but still this number will lie between like 0 to 1. 0 is the closest, 1 is the farthest apart. And this is cosine similarity, so that's the angle between the two. And this is still close, but this is still a little bit farther apart, right?
Yeah, that's fantastic.
All
Man, what
right.
else? This is starting to get fun. Do you have any more demos for us?
Yes, I do. In fact, on the topic of demos,
Nice.
so this was a little bit of a fun exercise. Let me, everyone, just bid a goodbye to our friends here. I'm just gonna hide them. They've had their playtime, right? So let's get into the real world a little bit. So in
Cool.
this
Yeah.
case, what's happening is, let me actually show you this example. So typically, like the application of these multimodal large language models, it'll typically be in processing these unstructured documents in the form of PDFs. Typically, like imagine you're a financial services customer and you get these or you are like a home lending application company, right? You basically look at applicants, thousands of applications every day. You get these documents from applicants who are potential home buyers, like their earning statements in this case. It could be their tax documents, it could be their paycheck, right? This is all very common. This is like, if I zoom out here a little bit, this is their driving license to just give them a little bit of like their identity. There's, of course, their tax forms. There'll be like a 1099 dividends and distribution sort of form, 1099 div. There'll be like this whole lending package that you'll get probably like every day and thousands of these, which is where you
Yeah.
have to take an informed decision based on the information in these documents, whether to approve or deny the loan, right? That's the example we're working with. So in that case, of course, like the text-based embedding models do a great job in parsing through the text and looking at the paragraphs, looking at the chunks, etc., etc. But then when it comes to like tables, when it comes to these financial documents, you'll see there's a lot of tables, there's a lot of charts, there's pie charts, there's graphs, etc., etc. And these text embedding models tend to be very lossy, right? They will not capture everything which is there. And for a financial services customer or a bank, it's very important to capture to the detail, to the right decimal point, what's the credit history, what is their credit score, how much do they owe, are there any faults, are there any penalties on their loan application,
I'm
right?
painfully aware
So,
of all of that, Cheyenne.
yes, I'm sure this is a huge pain in the industry today. This is very common for our customers. And in fact, to solve that problem, there are a couple of different approaches that we can take, right? So this on this diagram, you'll see the top sort of flow is the option one and option two parts here. These are where you actually use a multimodal embedding model, right? So you're looking at a document which consists of images, tables, text, potentially something more. But financial customers or healthcare documents will typically have these kind of multimodality within them. So in this case, if you look at a multimodal embedding, you can, using again LangChain's multi-vector retriever, you can actually embed both the images and the text chunks and the tables chunks all together. But then the challenge is whatever multimodal embedding models we have out there today, they aren't as good, right? So I've tested these very heavily in whatever is available today. More often than not, I have not been very happy with the results in the sense of the way they parse the text. They're very lossy, right? There's a lot of data that is lost, and in essence, the key financial numbers that we're looking at are lost. So to counter that problem, we do a different approach, right? So in this flow below, what we do is we take these, again, these documents, and we use a multi-vector retriever to summarize our image, our tables, and our text using a summarizer. We can do this via Python tools, etc. The image is summarized separately. The table and the text is summarized separately, and they are thrown into the vector database to get from the multi-vector retrieval. Right. Once they're thrown into the vector database, of course, the retrieval again becomes magic. That's the magic that's Claude 3 or Claude 3 Sonnet or Haiku or any of the others like Cohere or Meta or Llama. All of these models will do. And that's where you need like a multimodal LLM because you're looking at image retrieval plus the text and table retrieval. Right. So all the cases you'll always be using a multimodal LLM, but then the text embedding here to segregate and segment the image summary as a text plus like the table and text summary is very critical to understand. I know there was a lot of talk there. Just take a pause here. Any questions?
No, the only question is it better than Pinecone? I don't know. Someone really likes Pinecone or
Someone
not.
really likes Pinecone.
But let
Yeah.
me here. Let me take that. So Postgres, for those who don't know, Postgres has actually been around for almost 40 years. It started out as a project at University of California, Berkeley in 1985. Actually, I think 1986 was the first release. I'm the same age as Postgres, which I kind of find cool and ironic. But what's happened, Postgres was open source in 1996, and what's happened over the past, nearly 30 years is all these features have been added to Postgres, to be able to handle workloads, large and small. But one of the biggest superpowers of Postgres is its extensibility. You're able to basically add functionality to Postgres without forking the database, and it's created this whole world of extensions. Like you have extensions that make Postgres into a geospatial search database. So many maps around you are just created with Postgres, as the backing storage system. And this is where we see things like pgvector, which allow for all of this to happen. And what I'd like to say is that when you're using an extension like pgvector with Postgres, you have that extension and everything that Postgres has to offer. So it goes beyond just vector search. You have vector search, full text search, geospatial search, boring old lookups like very basic SQL statements. Then there's all the operational features around Postgres that let you help manage the database, and that's where something like Amazon Aurora comes in to help because it manages all of that for you, and adds other features that allow you to help you to scale, such as Amazon Aurora Serverless V2, which basically scales with your workload. Amazon Global Database, which lets you deploy a multi-region setup of your database and allows you to ensure your data is available in throughout multiple regions, for disaster recovery or even just spreading your workload out. And things like Amazon Aurora Optimized Reads, which has been the feature that we discussed about extensively today, letting you scale your workloads further, and many, many more. So the way I look at it is that when you use Postgres for building your generative AI applications, you get so much more than just vector search. You get a full database, and that's where the powerful.
I would say if you have your data in relational database, why not put your embeddings right there? Makes sense to me, man.
Yeah,
exactly. All right, well, back to Cheyenne, your demo. Thanks for that answer, Jonathan. That was helpful. Hopefully, producer of Joy got her answer. Sounds like it is better than Pinecone. Or at least that's our opinion.
Awesome. Yeah, I think so. Back to the demo. So you'll see that I'm trying to do a bunch of code to basically now sample these images in the document. Remember we have our lending package, which consists of things like our tax statements, driver's license, 1099 dividends, account statements, payroll, and so on and so forth, right? So this is all that. Now, what we're doing is
creating... By the way, I do want to call this out. Everybody sees this text on their screen.
Yes.
If you want to get that $20 and try some of this out yourself, go take that CSAT survey. Let us know how we did, and the first 50 people are going to get $20. So on awesome. AWS credits. All right. Sorry, Cheyenne. Go ahead.
I would take that. I would do that first. So let them do that, and then come back to this. All right. So here, if you see, I'm doing a bunch of code again. This is a standard sort of API call using Bedrock and LangChain, pretty standard. This is the key information, right? So the prompt is actually going to drive a lot of your responses around what's the tailored information that you're looking for. And Anthropic, Claude is the model that we're using. Anthropic provides a really sophisticated way of prompting your LLMs to give it the response that you need, right? So there's a huge field of sort of interest called prompt engineering. We can go deeper on it later, but then I'm just asking it to summarize all the details in the image, focus on the stats, make sure to include any time periods, etc., to be more precise, right? So in this case, I'm going to run this. This is my homeowner's insurance application. This is how it looks like. We have a person called Alejandro Rosales with a co-applicant, Jane Doe, who's potentially looking to buy a new house, right? And it also note that it has its auto claims, number of at-fault claims, number of not at-fault claims, major or minor violations, etc. So the first step is to create a summary of this image. So this is what you'll see using Claude 3 Sonnet. Pretty good detail. And if I go here, scroll to the right, I'll zoom in a little bit to make it a little bit clearer. So you'll see the application is for Alejandro Rosales, who's applying for home insurance coverage. blah, blah, blah. Let's do a fact check real quick, right? So number of auto accidents at fault 3, not at fault 1. So you'll see number of auto accidents at fault 3, not at fault 1. Number of violations, major 2 violations, minor 1, major 2, minor 1. Looks good. All right, so let's add this data into the vector store. So here we are using standard code to actually put this into our vector DB, which is PG Vector on Amazon Aurora. I've created a bunch of environment variables from my database to shove this data into the vector DB store. And I've actually run this already, so blah, blah, blah. Now, as a approver for this application, as a lender of this home buying application, I'm going to start asking questions, right? So give me a detailed breakdown of this person's home insurance application. Let me run this. So, okay, I'm getting 4 retrieval documents, which are closest to matching. Let's see. So this is the image that was pulled. I'm going to do my RAG pipeline here. This is, again, standard LangChain common expression language. But then here is the magic, right? So give me a detailed breakdown of XYZ home insurance application. Within a few seconds, you'll see this less than a minute, how quickly it can actually summarize both the image as well as the response to my question very clearly for me to take a decision, right? So let's see. So this is the image that I got. This is home insurance application correct. This is the exact match. And here are my summarized sort of details. I'm going to make it a scrollable element just to scroll through a little easily. You'll see, based on the provided home insurance application, here's Alejandro Rosales. Here are his details. This is the primary applicant, but then I have a co-applicant, Jane Doe, their details, auto claims, number of at-fault auto accidents, major, minor violations, so on and so forth. Right.
That's
so
fantastic.
this is pretty cool. Now,
Yeah.
let's say I want to check out a different form, right? So I want to look at their tax details. Okay, this looks good. I mean, homeowners insurance application is pretty good. But I want to also do a little bit of analysis on their tax-related information. In this case, I have a 1099 div. So I'll just change this question to retrieve the most similar documents from my knowledge base. We are getting about 4. I'm going to run these all together. You'll see this div form rightly retrieved here. And I'm going to run through the RAG pipeline again, and then sort of change this question to be my exact question for the tax form.
Yeah.
And you'll again see sort of how clearly, and we'll do like some fact checking based on the responses, but you'll see how clearly I can actually distill the noise from that document, because these are very dry forms, right? We are looking at these humongous sort of thousands every day. So this is my 1099 div. I'll see this very clear sort of, the form is for recipient Ana Carolina Silva, residing at whatever XYZ address. Let's actually now fact check. So Anna received $1,000 in total ordinary dividends. And I'll also do maybe one more. Let's say the form shows $8,000 in total capital gain. So remember, total ordinary dividends, $1,000, total capital gain, $8,000. Let's go back. We'll see, here we go. So ordinary dividends, 1,000. We have dividends here, 8,000. We have a few other things. Let's actually go back. She also received $500 in qualified dividends, which are taxed at a lower rate. Let's go back, verify this information. So qualified dividends are 500, capped at a lower tax rate. Ana Carolina Silva, 123 Any Street. So you can just go crazy, right? You can see
This stuff is impressive, man. I want this app to do my taxes next time. I'm coming to you for that. All right. Well, I know we're running out of time. We just have 6 more minutes. But I have a very important question for you, Jonathan. I know you talked about some of the performance things. We keep hearing about databases are slow and all that kind of good stuff. So if we pump all of this data into Postgres, how is this going to perform? Can you tell us about that? What have we done to improve some of the performance?
Databases are slow. I've never.
That's
heard
all I
that.
hear about, man.
Databases are slow. I think the great thing about databases is that they are, high performance engines. And sure, and if you see if we step back from Gen AI for a sec, databases power the world. Like all of our data resides somewhere, and we need to be able to retrieve it fairly efficiently. So if you pull up my screen real quick, I can actually show you some charts about PG vector performance in general, and just highlight a few things. So as I mentioned, AWS is the second largest contributor to PG Vector. Like, we believe in it, we love it. We contribute heavily to it. And as I mentioned before, one of the advantages about using PG Vector is that you have Postgres, and Postgres is a database that scales. It scales vertically very well, which means that if you add, as your workload increases and you increase your instance size, Postgres will scale with it. And PG Vector does this as well. If you look at a lot of the vector benchmarks out there, they tend to show, well, two things. One, they show things that are just entirely in-memory systems, or they show like one connection at a time. When in the real world, you're sending a lot of connections, a lot of, basically making a lot of queries simultaneously, which is called concurrency.
Thousands, hundreds of thousands sometimes.
Yep, and this is where PG Vector works very well. So on this particular instance with this particular data set, we see that we can get tens of thousands of queries per second, even as we add more connections to it, and the throughput stays very good regardless of that relevancy target we're looking for. And beyond that, because of the investments that the PG Vector community has made, we've seen that performance improve over the past year. One thing I want to highlight is particular index building time. Index building is the most important part of getting highly relevant, very fast queries for your vector searches that you're doing as part of building your Gen AI applications. And we've seen an over 150x performance increase in the index build time, which is crucial because if you're able to get that data into your database faster and be able to get those highly relevant results, that makes your application that much better because that search experience is going to be great. Additionally,
the index building is pain, man. If it's going to be 150x faster, that's amazing.
Yeah. Additionally, we've seen a 30x improvement in query latency. And in this case, I took a little bit more to the extreme. I looked at the P99 latency, so effectively like your worst case scenario latency. And I used 99% recall, which is as close to getting that perfect answer as possible. And typically what happens is that you usually don't need as that level of recall. Usually like 90%, or in some cases 80% is good enough. But being able to see that you're able to get these super fast, highly relevant queries returned is great. And finally, just that cherry on top, we've talked about how Amazon Aurora optimized reads can improve performance up to 9x for memory constrained workloads. Here's the chart. We took a data set. We took 1 billion vectors, 1 billion with a B, put them into Amazon Aurora database. So one with optimized reads, one without. And we saw in particular, as we threw more concurrency and more clients at it, the performance gap certainly increased because we saw the Amazon Aurora optimized reads instance was outperforming the Amazon Aurora instance with optimized reads up to 9x. Once the workload no longer fit into memory. And that's a really important point because that basically means you can take your same instance and run it for a longer time at that instance size before you need to upsize it based upon your workload. It also means that you can scale your workloads even further on Amazon Aurora. So I think I think this is pretty cool that there's all sorts of ways that you can run
fantastic.
Small and large workloads on Amazon Aurora. Yeah.
Well, we have 2 minutes left. So what did we learn today? I mean, you can use your generative AI workloads with all the cool tools like Amazon Bedrock that Amazon provides you, and it's all API based, so it's all click. That means you're just paying for those API calls. Like Jonathan showed us, the Aurora Postgres database is going to scale. It's going to be super fast, and it continues to get faster. And you can use it in a serverless way, which means again you only pay for what you use. I'm impressed, man. I'm like I said, Cheyenne, thank you for all those demos and all those cool animals and giving us all this information, Jonathan. This was fantastic. Folks, thank you for attending. I hope you learned and you had a good time. We do this show every Thursday. So next Thursday, we're going to talk about DynamoDB. We're going to switch gears and talk about NoSQL, and we're going to talk about Zero ETL. So don't forget to dial in. Don't forget to take those surveys and claim your $20 in credits so you can go and try some of these things you're on. Again, thank you all for joining, and it was really nice to have both of you, Cheyenne and Jonathan. Thank you for your demos and sharing your knowledge. See you next time.
See you, everyone.
Take care.